This problem has a square plate which is given an angular velocity omega naught about an axis that passes through one of its vertices. It's on a rough surface, therefore there is friction in the problem. Therefore, this is going to stop rotating. And the time taken for that is t naught. The question is, now if the same plate is given the same angular velocity about an axis passing through its center, how long would it take to come to a complete stop? This square plate has an angular momentum about this axis, and that is equal to its moment of inertia about that axis, I naught into omega naught. Because the surface is rough, there is going to be friction at the base. So that's going to provide a torque about this axis, which is going to reduce this angular momentum to zero. So the change in angular momentum is I naught omega naught. That must be equal to the net torque provided by friction into the time taken for it to stop. Without using calculus to figure out the exact value of I naught and tau naught, we could say that they're going to depend on the quantities given in the problem. So m, l, and g, and also the coefficient of friction mu. Once we figure out the form of I naught and tau naught, we could take that over to the second case too. And in the second case, you're going to have a similar equation, and the change of angular momentum in this case would be the moment of inertia about the central axis, angular velocity initial, torque in this case, which is different than before, and therefore the time taken will also be different. Here, if you can figure out a way to break this piece and think about it with an axis through one corner, then the exact form of the moment of inertia I naught could also be used to figure out I2. Similarly, the torque about one corner due to friction should also relate to tau 2. So that's the central point. Once that is done, you could just take a ratio and figure out the value of the time taken for it to stop. We know that the dimensions of moment of inertia is mass into length square. The only parameter with dimensions of mass is the mass of the object. Only dimension of length is the length of the side. Therefore, I naught must be equal to ml square. There should be a numerical factor in front. We don't know that, and that is some k. And the k relates to the distribution of the mass with respect to this axis. We don't need that in this problem because you're going to take ratios and get rid of it. Similarly, let's look at the torque. If you take a small piece out here, that piece is at a distance r from the axis. Now this piece undergoes circular motion about this axis, and therefore the frictional force must be tangential. Now this is 90 degrees. Now that's a small frictional force out there. The small frictional force is going to depend on the normal. So if you draw the normal out there, that is in response to the mg. Therefore the small mass of that into g must be the normal force out there. Therefore the friction is going to be coefficient of friction into the small mass into g. Now this frictional force is tangential out there. The small amount of torque it's going to provide is the force, which is mu times dm into g, into the perpendicular distance from the axis. So we would need to integrate this to figure out the torque. But that's not what we're going to do because we just need the ratios. Therefore, the torque in this problem, mu and g are constants, and this has dimensions of mass and that length. So this term tau naught can only look like mu g, the mass into length. Now, if that integration is actually carried out, there will be a numerical factor in front. We don't know that, and therefore we are going to call it n. Now let's take this over to the second case. In this, the change is that the axis is through the center. And the central point here to solve this problem is just this recognition that this can be cut into 4 pieces. And as soon as that is done, you have an axis with respect to one of the squares at the vertex. exactly as it was for this. So these two are comparable. So the form of the moment of inertia and the torque should look the same for both of them. Once that is recognized, the moment of inertia in the second case must be equal to, what are the counterparts? The mass of this first one is 1/4 the mass. The length of the side is L by 2. Therefore, it must be equal to K into mass by 4 length by 2 whole square, because I2 has the same form as I0, because the axis has a similar geometry with respect to both of them. However, has to be multiplied by 4 because there are 4 such squares. As you can see, this can be written in terms of the original I0 divided by 4. Similarly, let's look at the torque in the second case. It has to have a similar form for one of the smaller squares, and therefore it looks like N mu G M by 4 into L by 2. There are 4 of them, therefore into 4. This looks very much like the original torque, but with a factor of 2 in the denominator. Let's take a ratio of equations 1 and 2 to figure out T2. So from 2 by 1, we would have T2 is equal to T0 into I2 by I0 into tau naught by tau 2. And as you can see, this looks like T0 divided by 2. So there we have it. That's the solution.